Aviation rules define visibility strictly. It is simply the greatest distance at which you can see and identify objects. We often associate bad weather with violent, unstable air, but rising air currents physically carry obscuring particles away, leaving the atmosphere crystal clear. The true threat to visibility hides in smooth, stable air, where stagnation traps dust, smoke, and moisture close to the ground in a hazy whiteout. Slant visibility creates an optical trap. Directly overhead, a runway looks clear through the thinnest cross-section of haze. But on final approach, your viewing angle changes, forcing your sight diagonally through thousands of feet of fog. The runway vanishes. Total atmospheric obscuration is rarely random. It is an exact thermodynamic mechanism governed by three precise variables: temperature, moisture, and wind. Relying on vertical visibility when assessing an airport is dangerous, because slant visibility will always be significantly worse by the time your wheels are down. To actually predict a whiteout, we have to look at the atmosphere's temperature profile. Particles that blind pilots, dust, industrial smoke, pollen, and sea spray, need specific conditions to remain suspended in the air. Normally, air temperature decreases with altitude, but when the ground cools rapidly overnight, or when descending high-pressure air warms up, a layer of warm air can settle directly above cooler surface air. This is a temperature inversion. This inverted temperature profile acts as a physical lid. Any air trying to rise from the surface immediately hits this warmer blanket and stops. Vertical convection currents are completely shut down. Without vertical mixing to blow them away, industrial smoke, car exhaust, and salt particles pool rapidly in the lower levels. They become trapped right at the surface. When you combine an inversion layer with industrial outputs, the result is dense smog. The abundance of combustion particles creates a dirty, stagnant soup that blocks out the sun and completely swallows city skylines. Because the inversion actively suppresses all rising air currents, flying through this trapped layer is typically perfectly smooth. The exact thermodynamic mechanism that guarantees a perfectly smooth flight is the very thing holding the obscuring particles in place. But dirt and smoke alone rarely drop visibility to zero. For that, the atmosphere needs water. As warm air moves horizontally across oceans or large lakes, a process called advection, it acts like a sponge, absorbing massive quantities of invisible water vapor. This readout represents an aviation METAR report, showing two crucial numbers: the ambient air temperature, here at 6 degrees Celsius, and the dew point, at 4 degrees. The dew point is the exact temperature at which that air parcel can no longer hold its invisible water vapor. As night falls and the Earth's surface loses heat, the ambient air cools. The gap between the temperature and the dew point begins to close. When the temperature hits the dew point exactly, the air reaches complete saturation. It forces the excess invisible vapor to physically condense onto the trapped dust and smoke particles, instantly transforming into millions of opaque, visible water droplets. In a hypothetical environment with absolutely no dust, the air might cool a few degrees past the dew point before anything happens. But real-world atmospheres are packed with condensation nuclei, triggering this phase change precisely at the threshold. If this exact cooling process occurs directly against the cold metal skin of an aircraft parked on the ramp, the water condenses there instead, leaving a coat of dew or solid frost. Tracking the temperature-dew point spread provides a perfect leading indicator. A narrowing spread tells a pilot exactly when the invisible moisture will turn into an opaque wall, dragging ceilings down with it. Once the air reaches full saturation, temperature steps back. The final factor that dictates what actually forms is pure mechanical wind velocity. We can see how wind speed controls visibility by looking at this model of an airfield under clear skies. This setup shows the baseline conditions for radiation fog, where the landmass radiates its heat away into space overnight. If the wind is absolutely calm, air acts as a poor conductor. Only the bottom 1 or 2 inches of air touching the ground actually cools to the dew point. Moisture condenses directly onto the grass as dew or frost, while the air above remains completely clear. But if you introduce a light breeze of 5 to 7 knots, gentle turbulence starts rolling the cold, saturated surface air upward. This mixing thickens the layer, generating a dense bank of radiation fog that swallows the entire runway. Push that wind above 15 knots, and the mechanical turbulence becomes too strong. It violently mixes drier air down into the fog and physically lifts the saturated mass off the surface. Surface visibility clears up, but a low stratus cloud ceiling forms overhead. Because the ocean retains a fairly constant temperature and does not cool rapidly overnight, radiation fog is almost entirely restricted to landmasses. Knowing the 5 to 7 knot rule allows you to predict how a cold night will end. Zero wind leaves wet grass, while a light breeze ensures a completely closed airport. Radiation fog requires vertical cooling from the ground up, but the atmosphere also generates fog dynamically through horizontal movement, known as advection fog. If a wind continuously drives a warm, moist air mass off an ocean and over a significantly colder land surface, the bottom of that air mass is chilled below its dew point. Because advection fog is actively fueled by a moving air mass, it survives easily in winds up to 15 knots and can form abruptly in the middle of the day, regardless of cloud cover. When that horizontal wind pushes moist air into mountainous terrain, it triggers upslope fog. The terrain physically forces the air upward, dropping the pressure and chilling the air adiabatically until it hits saturation. Saturated environments can also form from severe temperature clashes, like warm rain falling into cooler air ahead of a front, slowly evaporating and saturating the cold air. In extreme polar regions, we see the inverse, steam fog. When frigid Arctic air blows over a comparatively warm, open crack in the ice, the water rapidly evaporates into the cold airstream, condensing instantly into thick, violent sea smoke. Radiation fog reliably burns off as the morning sun heats the ground, but advection and upslope fogs are locked into the wind. They will hold an airport at zero visibility relentlessly until the wind itself either stops or reverses direction. Atmospheric obscuration relies entirely on 3 intersecting physical mechanisms: a stable layer to trap particles, a closing dew point spread to reach saturation, and wind to dictate the final structure. Mapping these variables onto a visibility matrix, the horizontal axis measures wind speed, the vertical tracks cooling mechanisms. In the lower left, surface cooling and a light breeze form radiation fog. Higher wind and horizontal motion create advection fog. Maximum wind lifts fog into stratus clouds. The operational strategy is straightforward. Check the METAR to see how rapidly the temperature is approaching the dew point, log the wind velocity, and examine the local terrain for slopes or large bodies of water. Often, the only escape from this trapped atmospheric soup is climbing. Punching through the inversion layer leaves the smog below, breaking into smooth, sunlit skies. Total obscuration is an exact thermodynamic equation. By measuring the inputs of moisture, temperature, and wind, you stop reacting to sudden whiteouts on final approach, and you start predicting the state of the lower atmosphere long before you even start the engine.